Okay, good morning. So today we are on lecture 8. So in the last class we just got started on the topic of boundary layers. This is the page from the last discussion in lecture 7. So we are going to proceed with that, but before I do that, are there any questions? You're all working on homework 1, right? Is it going okay? Okay, good. So let's press on. So we talked about boundary layers, and so it's just a thin layer adjoining the surface. Inside this layer, the velocity goes from 0 at the surface, which is called the no slip condition, and from there as you go in the normal direction to the surface, the velocity increases until it reaches the edge velocity, and this kind of a plot is called a velocity profile plot. So broadly we can classify boundary layers into a few different states. So very broadly they can be either laminar or turbulent. And each of this can be attached or separated. Now there is a common sort of misunderstanding about some of these things. So people generally, instead of saying separated boundary layer, people tend to say turbulent boundary layer, or when they mean turbulent boundary layer, they say separated boundary layer. So they are very distinctly different. Okay, so don't confuse turbulent and separated. You can have attached turbulent boundary layer, and most airplanes in normal cruising flight have attached turbulent boundary layer, and that's completely okay. We're going to see more of this shortly. But turbulent boundary layer is not bad at all. It's actually a very normal boundary layer state, even in cruise condition, in efficient cruise condition. Likewise, some people may get confused between laminar and attached. Again, those are different states. So we'll talk about all this today. Okay, so first let's talk about attached versus separated boundary layers. Again, I'm just going to talk about this in overview form. So I'll use the example of an airfoil at somewhat high angle of attack. So we'll talk about a typical boundary layer development. On an airfoil at high alpha condition. This could be near stall. So in a state like this, there is going to be probably attached boundary layer on the upper surface for some distance, and then at some point the boundary layer separates, forming this separated region, something like this. And then here you will have sort of unsteady flow, you might have vortex shedding and things like that. So this part is called is attached boundary layer, and this part is called separated boundary layer. And here is the onset of separation. Okay, so what exactly distinguishes the boundary layer behavior or characteristics between attached and separated? And so for that we can look at the velocity profile plot. So I'm going to draw y over delta versus u over ue, and the edge of the boundary layer will correspond to 1, 1 on this kind of a plot. And we have seen this before, right? So this is going to be a velocity profile like this, just like we saw in the last class. So the velocity in the normal direction increases from 0 to ue at the edge of the boundary layer. So this is attached boundary layer. This could be laminar or turbulent. Now reversed boundary layer will look something like this. So in a reversed boundary layer, you will still have zero velocity right at the surface, but as you go in the normal direction away from the surface, you will have reversed flow. So the flow will actually start going, will be flowing in the backward direction for a small height, and then it changes direction and starts going in the usual direction of the outside flow. So this is what happens if you go in the normal direction from here. So if I go in the normal direction, inside this a portion of this boundary layer, the flow will be opposite to the outer flow direction. Right, then it turns around, no, it doesn't turn around, but the plot turns around and has positive velocity in the direction tangential to the surface. So this is reversed flow at the surface, and this is separated boundary layer velocity profile. Here again, this could happen both for laminar and turbulent boundary layers. So don't get confused between these two things. So what we are talking about here is just attached versus separated boundary layer. This has got nothing to do with whether it's laminar or turbulent. Okay, so this is attached versus separated. Now let's look at laminar versus turbulent boundary layer. So broadly speaking, laminar boundary layer is one in which the flow path lines so if I have a surface and you have laminar boundary layer, these path lines do not cross each other. So turbulent boundary layer is pretty much the opposite. So if you take a similar picture for turbulent boundary layer, here's the surface, and the path lines will cross each other as the particles flow along. So the flow inside this is also unsteady, which means if you go and measure using some kind of hot wire anemometer, if you go and measure the velocity as a function of time, it won't be a steady line. So if you measure this, it will be a constant, maybe very small fluctuation, but here there will be large fluctuation. That's because the particles are all not moving steadily. They're moving through the boundary layer up and down, and their velocity is changing with time. And that's the definition of turbulent boundary layer. So let's look at how the velocity profiles look for laminar and turbulent boundary layers. So laminar boundary layer may look something like this. Whereas a turbulent boundary layer, so this is laminar. Whereas a turbulent boundary layer will be fuller, so it will be more like this. So the actual height of the boundary layer will depend on where along the chord you look at, and the thickness will vary along the chord. We are looking at non-dimensional thickness and non-dimensional U over UE. So it turns out that this slope of this graph at the wall has an important significance. So the shear stress at the wall, it's tau is the symbol for shear stress. So this is symbol, so Greek letter tau, T-A-U. So tau at the wall is really the symbol for shear stress at the wall. You can have shear stress even in the fluid, not at the wall, but to make sure we are talking about the wall, we put subscript wall. So shear stress at the wall, it turns out that that's equal to mu times du dy at the wall. And mu is coefficient of dynamic viscosity. Right, so this du is the velocity parallel to the surface, component of velocity parallel to surface, and y is the direction normal to the surface. And so that's pretty much what we are doing here. So which boundary layer has greater du dy? Turbulent or laminar? Laminar? I heard laminar, turbulent. You guys don't want to vote. I mean, du dy, come on, look at this and tell me which is higher, du dy. So go for a small y and see which one has got greater du. Anybody want to change answers? You changed an answer, right? Okay, u equals 0 here, so you go for a small y up in this plot, and laminar has got some du, turbulent has got more du. So du dy is greater for turbulent boundary layer, right? This may be confusing maybe because we are plotting u on the horizontal axis and y on the vertical axis. Normally you think of dy dx as the slope, and everybody kind of pictorially you know what it is. But here, just for the reason we are plotting u horizontally is because flow is you usually draw flow this way, and y is normal to the surface. So if this is a surface, you're going in this direction. So you can connect it with the airfoil picture, for example. But then when you have to calculate du dy, you flip what you normally think about as the slope. And so turbulent boundary layer has greater du dy at the wall than laminar. And therefore it has greater wall shear stress and higher skin friction coefficient. Right? We saw the relationship between skin friction and wall shear earlier. So skin friction coefficient is simply wall shear stress divided by half rho v squared and a small area on the surface. So go back and look at this if you don't remember. So this is the difference between laminar and turbulent flow. And here I've drawn attached for attached laminar and turbulent so just because a flow is turbulent, it's not that it's bad or anything. You can have attached turbulent flow, you can have separated turbulent flow, and likewise for laminar. Okay, so what controls a lot of the boundary layer is the velocity distribution, and more specifically something called velocity gradient. So let's look at velocity gradient. What is velocity gradient? So velocity gradients are different from velocity profiles. So velocity gradient is essentially the slope of the velocity distribution at some point. So let's plot that. So let's say this is an example velocity distribution. Like we mentioned earlier, velocity distribution is the velocity along the surface of the airfoil from leading edge to trailing edge on the upper and lower surfaces. So this is different from velocity profile, right? Velocity profile is as you go up from the surface in that thin layer, how does velocity, tangential velocity change as you go up in the normal direction. So velocity gradient is simply the slope of this. And so you can say in these parts of the airfoil, as you go in the increasing x direction, velocity increases. So in these parts of the airfoil, velocity gradient is favorable. So I'm drawing here the slope. And in some other parts you will have a negative slope, which means as x increases, velocity decreases. And here velocity gradients are adverse. I mean, we could say positive and negative. We could have said velocity gradients are positive, velocity gradients are negative. But in usual airfoil discussions, we say favorable and adverse. And there's a reason for that. And that becomes clear when we draw the pressure distributions or CP distributions. So we have seen earlier that you can take a velocity distribution and convert it to CP distribution. And normally you plot the CP distribution upside down, right? So you will say is +1 and then negative goes up. And a typical CP distribution, I'm going to try to draw something resembling this, but it won't be, it's not an exact conversion. It's just a sketch. So you might have a CP distribution that if it's for this velocity distribution, it'll probably look something like this. And then okay, it's not an exact translation, but it's intended to be somewhat similar. Now, so if you take this point on the airfoil, that's this point on the CP distribution, and the slope is like this, right? But because the CP scale is upside down, this is actually, it's really a negative slope. As x increases, CP decreases. But because we plot it upside down, it looks the same, right, on these 2 points. So here, this what you call as a positive velocity gradient is really a negative CP gradient. And because people use these plots kind of interchangeably, some people plot velocity, some people plot CP, they really kind of mean the same thing in terms of interpretation. So if you say positive, negative, you have to keep on switching. Right? What is positive in velocity will be negative in CP, and it just causes confusion. And I think that's the reason we think about these as favorable and adverse. So these points have favorable pressure gradients. And these points have adverse gradients. So we look at these kind of plots quite a bit throughout this course. So get used to referring to these kind of behaviors as favorable gradients, whether in velocity or CP, it's the same thing. And these, when the curve goes down, that's an adverse pressure gradient, same thing, whether in velocity or pressure. And this holds only because we are plotting CP upside down. There's also another reason, maybe more important reason why these names are given, favorable and adverse. It's because they control how much momentum the boundary layer loses or gains as it flows down the surface. So if you take a boundary layer flowing along the surface, so let's say there's an airfoil and you have the boundary layer is like this. I'm drawing a very thick boundary layer just so you can see. If you take a particle here, so here's the surface, or let's just take 2 stations in the boundary layer. There is going to be shear stress on the surface because the flow is, we saw that there's going to be shear stress anytime there is a du dy, and there is always a du dy, right? So if it's attached flow, the du dy is positive, so there's shear stress on the surface. That shear stress acts in this direction for the surface, but for the boundary layer, it acts in this direction. So the flow causes a scrubbing stress on the surface in this direction, but the surface retards the flow, right? So it causes a scrubbing kind of stress in this direction. So if you did not have anything else going on, just this itself will cause a momentum loss for the flow. As it goes from here to here, there is a force acting this way, so it's causing a momentum change. And so the boundary layer, just if you take this as a big fluid element, as it goes down, it's losing momentum. But on top of that, there is pressure. So you can think of pressure acting on two sides. So if the pressure here is less than the pressure here, that means this has suction, right? So there's a net force acting this way. So favorable pressure gradient will be like this. So okay, let me label this. This is shear stress on the fluid at the surface. And this is the pressure on the aft face of a boundary layer element. I'm just using the concept of a boundary layer element kind of loosely. And this is the forward pressure on the forward face. Right, so the flow is in this direction. So a favorable gradient is where you will have more pressure here and less pressure here. So in other words, dP dx, so if this is the x direction, dP dx is less than 0. So it's going into more suction. So the flow will want to go along the surface, right? Because there's suction kind of pulling it in the direction of the flow. So this is called favorable pressure gradient is where dP dx is negative, which means the pressure gradient supports the flow. It encourages the boundary layer to keep flowing. But an adverse pressure gradient is the opposite. So if I take this as the boundary layer, the pressure increases as the flow progresses downstream. So here dP dx is greater than 0. Right, so if you take a particle here, pressure is going to act on two sides. If the pressure helps the flow, that's favorable. If the pressure kind of retards the flow, it tries to slow down the flow. So this is adverse pressure gradient. And so favorable pressure gradient, dP dx being negative, will look like this in a CP plot. An adverse pressure gradient will look like this in the CP plot. So obviously, if the boundary layer, if to keep the boundary layer healthy and attached, we would like favorable pressure gradient, but you can never have always favorable pressure gradient because an airfoil pressure gradient has to close. You may have favorable gradient in the beginning, but then eventually there will be adverse pressure gradient. So this, as long as the boundary layer has good momentum when it comes to the adverse pressure gradient, it will be fine, because think about it as these fluid particles in the boundary layer. If they have a lot of momentum, it can withstand the shear stress and the adverse pressure gradient, and it will lose momentum, but it won't completely lose it all the way to the trailing edge. So that's when it stays attached. But if the boundary layer does not have enough momentum when it encounters adverse pressure gradient, then already it's low in momentum, and then it has adverse pressure gradient, and so it's going to lose momentum, it will become zero velocity, and then it will even start flowing the other way around. that's when flow separation, boundary layer separation happens. And that we will see soon. That's what will happen when this is at high angle of attack. So on the upper surface, you may have adverse pressure gradient all the way from the leading edge. And so by the time it comes to the trailing edge, the boundary layer can't stay attached. It will start having reversed flow. And eventually it will separate. So anyway, that's the reason for calling these favorable and adverse. Okay, so I can make a note here about one of the things you do in homework 1. In homework 1, you'll be plotting velocity distributions. And in the data files I've given you, the sign convention is in a particular way, and I need to explain that. So if the flow is attached on both surfaces, so the flow will be going like this, right? In the files provided, on this side of the stagnation point and most of the upper surface, this direction of velocity is called positive. And on the lower surface, on this side of the stagnation point, even though the flow is going in the normal, usual direction, attached flow, this velocity is called negative. That's just the way the sign convention is. And the reason for doing that is because, I think part of it is because with the velocity distribution, you can actually find the stagnation point by finding out where the sign crosses. So you can find out where the zero occurs and find the stagnation point. So if you plot this velocity distribution, it will look like this. If you just plot it as it is in the data, the upper surface will look like this and the lower surface will look like this. So U over UE as per the data. But this is not how our usual velocity distribution looks, right? Our velocity distribution should look like this. Should look like this. And that's how I want you to plot it, because it's as only if we make the plots always in the same way, we will be able to train ourselves to interpret it. So if you plot velocity distributions one way today, tomorrow you plot it another way, you're not going to be able to say anything about them. So I want you to, even though the data is like this, I want you to plot it correctly, something like this. And this is simply the absolute value of U over UE. So when you make the plots, take the data from the files and do the absolute value and then plot it, and then it will look fine. So please pay attention to this, because if you plot it like this, I mean, that's not what we're doing in this course, and so don't, I mean, I'm going to take some points off definitely. Okay. So we talked about these velocity gradients, and one of the interesting points about velocity gradients is how they change with alpha. So let's plot velocity distribution for two angles of attack. So let's say this is for a small angle of attack. Velocity on the upper and lower surface. And let's plot for a much higher angle of attack. For a much higher angle of attack, it will probably be something like this. And we saw this earlier, right? Some couple of lectures back, I think, we saw how as you increase alpha, the gap between the upper and lower surface curves will increase, and that's how lift increases. And the way the gap increases is there's more increase near the leading edge and less increase as you go towards the trailing edge. And that's how pitching moment about the aerodynamic center, the coefficient of pitching moment doesn't change with angle of attack. Now, this also results in a sort of universal rule for velocity gradient. And gradient is the one that controls boundary layer behavior. So that's important. So velocity gradients and this is for inviscid flow. And inviscid velocity distributions control boundary layer behavior. Velocity gradients always become more adverse, or they may become less favorable on the upper surface with increasing angle of attack. And the opposite behavior on the lower surface with increasing alpha. So you can see this in this plot, right? At small angle of attack, let's take the upper surface curves. These two are the upper surface curves. Near the leading edge, you have very favorable gradient. And it becomes less favorable and then it becomes adverse as it increases angle of attack. That's true even for the trailing edge. It's already adverse, but it becomes more adverse when you increase angle of attack. On the lower surface, it's the opposite. So as you increase angle of attack, it becomes more favorable or less adverse. So this is a behavior that's going to be very important as we go and analyze airfoils, and even when we go to design airfoils, understanding this is one of the key points. Okay, so with this now we are going to go and look at some general trends for various kinds of airfoils. So the next few topics are we will look at typical boundary layer development. We'll take some cases. So we'll say a low alpha case, which is like a cruise condition. For general aviation type airplanes. And these are we'll be looking at natural laminar flow examples. Then we'll look at high alpha, which is near stall, for something similar. And then we'll look at a different regime. We'll look at low to moderate alpha for low Reynolds number airfoils. And these are the airfoils that may be used on UAVs and drones and even some full-scale sailplanes. So these will help us to understand the trade-offs between laminar and turbulent flow, especially in this. And here we'll talk about attached versus separated flow. And then here we'll come to separated laminar flow and reattachment. So it helps us to put together different boundary layer states. Okay, so let's take the first case. So GA is general aviation. Although not all GA airfoils are NLF. Okay, so we are going to consider an NLF type airfoil. NLF is natural laminar flow, but many GA airfoils don't have extended laminar flow. So this is an NLF airfoil for GA application. And the Reynolds number is of the order of 3 to 6 million. So the kind of airplanes we are talking about are like fast 2-seaters, 4-seaters, and 6-seaters. It's only in the past like 20 years or so that people have started looking at using natural laminar flow airfoils for these kind of airplanes, although not everybody has adopted them. Some people just stick to regular turbulent flow airfoils. The benefit of laminar flow airfoils is that it gives less drag, but then you can't have too many surface imperfections. So in the olden day airplanes like Cessnas, metal construction airplanes, they use rivets for joining the wing skins to the spars or to each other. And so those rivets cause surface imperfections, and it doesn't support laminar flow. So we'll look at all these things as we go along. And that's the reason many airplanes don't have NLF airfoils. So to use NLF airfoils, you have to have construction that's free of imperfections and that's fairly smooth, and that's become possible largely with composite construction. So fiberglass, carbon fiber airplanes have smooth wing skins. They don't have rivets. And in these, you can use NLF airfoils. Okay, but without going too much into those things, let's just start looking at aerodynamic characteristics. So we're plotting CP distribution, and as always, CP distribution goes negative up. So you may have a CP distribution that looks like this. And to connect it with the airfoil, let's plot the airfoil below. So the airfoil will probably look like this. It's just a sketch, so I mean, don't think that this and this will exactly correspond. I'm just sketching something. So what do you think will happen to the boundary layer? So boundary layers always start off laminar at the stagnation point. So stagnation point maybe somewhere here. So boundary layer will start off laminar on both upper and lower surfaces. And what kind of gradient is this? It's favorable gradient. And so at these Reynolds numbers, the boundary layer will definitely be attached, but it will also be laminar. So favorable gradient, we'll see later on, helps support laminar boundary layer. And then when the laminar boundary layer comes here, what happens in this region on the upper surface? Is this favorable or adverse? It's adverse, right? And so it turns out that the boundary layer will become turbulent, and I'm going to use a squiggly line to denote turbulent flow. It doesn't mean that the flow will actually be squiggly. It's just a graphical way of representing turbulent flow for our discussion. So this is turbulent boundary layer, this part. And on the lower surface too, you will have laminar flow up to about maybe here, and in this case there is adverse pressure gradient here. So you will have turbulent boundary layer in this portion. So these two are turbulent boundary layer, and these two are laminar boundary layers. That's just this example, right? It's not like all GA airfoils are going to be this way. I'm just selecting some examples for discussion. And T, I'm using this letter T to denote transition. So T equals transition from laminar BL to turbulent BL. In this example and in such situations, the boundary layer is always attached. So even though it's turbulent, it's not bad, it's attached. And this is a very typical CP distribution and boundary layer development for a natural laminar flow airfoil at a low angle of attack. So let's summarize the main features. So first, there is attached flow everywhere, which means when I say attached flow, there is no separated boundary layer. And not only is the flow attached, but the boundary layers are usually very thin. So the boundary layers are thin. Pressure drag is negligible. What is the other kind of drag? But shear stress, yeah, that's the source, but what is that drag called? Yes, it's called skin friction drag. You're right about the source. So pressure drag and skin friction drag, those are the two types of drags. Because the aerodynamic forces on an airfoil come from two sources, pressure and skin friction. So really, in terms of drag, it's the skin friction drag that's the dominant contribution in this situation. And these are all for the NLF airfoil at low alpha. So all of these correspond to that previous page situation we are talking about. So these are the kind of things you're looking at in homework 1-2. You're looking at pressure drag, you're looking at skin friction drag. What is pressure drag? Have we talked about it? What is pressure drag? Go ahead, somebody say. Doesn't matter if...
pressure distribution.
Yeah, it's the component of the force arising purely from the pressure distribution, the component of the force in the V infinity direction. That's pressure drag. It's a contribution to drag due to pressures. So this is pressure drag. So let me pose a question. What is pressure drag in inviscid flow? So inviscid flow is where there is no viscosity, right? So no boundary layers. What is pressure drag? 0. Where do we get that from? Right? Boundary layer, absence of boundary layer just means there's no skin friction, right? There's no rubbing, scrubbing kind of stress. Can you attach a name or concept or... Yeah, D'Alembert's paradox, right? Have you heard about that? I think you should have. Anyway, in inviscid flow, pressure drag is 0. This is only for airfoils. For wings, pressure drag is not 0. What is it called? Yeah, induced drag is actually a form of pressure drag. So even in inviscid flow for a wing, you will have pressure drag, and that's called induced drag. So at least for steady airfoil problems, pressure drag is 0 in inviscid flow. So if you want to look at this in more detail, review this concept called D'Alembert's paradox. And this paradox comes because inviscid pressure distribution should integrate to give only lift and no drag. So this was known many years back, maybe I'm thinking 200 years back or something, where people figured out that if you do an inviscid solution, which they could do by solving the Laplace equation for flow around a cylinder or any kind of object, 2D flow, they could solve the inviscid flow and they could get the solution, and that would always give 0 drag. But then everybody knew from practical experience that if you put a body in flow, the drag wasn't 0. And so that was the paradox. And D'Alembert, I think, brought this out, and he posed the paradox as how come it is that when we solve the flow past a body, you get 0 drag, but real flows have drag. And this was before the concept of boundary layers was discovered by Prandtl, and Prandtl was the one who came up with the idea of there is actually this thing called boundary layer, and because of boundary layers, the flow around a body does not match up with inviscid prediction unless the body is streamlined like an airfoil and at low angle of attack. And only then I think we started understanding that the difference between an inviscid flow and a viscous flow and the whole idea behind boundary layers. So inviscid pressure distribution should give 0 drag, but then in your homework, even in part A, where I give you an inviscid pressure distribution, you integrate it and you get a tiny amount of drag, right? That's just numerical error. It's round off errors because we don't have a perfect pressure distribution. We are dividing the airfoil into number of segments. Even if it's 200 segments, there's going to be small round off errors because of discretization and some angle calculations and things like that. So you end up getting a small amount of error. But if everything was done completely perfectly, you will get 0 drag. Any questions here? So if real flow does not match up with inviscid flow, why is it that we are even studying inviscid flow? Is it just one theoretical concept that's of no use? Anybody know? We've talked maybe a little bit about this before. Why do we even study inviscid flow if it's not reality? Yeah, that's the whole point. First of all, inviscid flows are so much easier to solve than viscous flows. I mean, even after so much progress in CFD, solving a viscous flow with some computational fluid dynamics, with all detailed Navier-Stokes solution is still a challenge. We just can't seem to predict with full confidence viscous flows past any kind of body, right? There's always some uncertainty, and people are going to more and more complicated CFD because you're trying to capture everything that goes on in real life flows. So in comparison, inviscid flows are so much easier. It's like almost we have come to the point where you can get an inviscid flow about even an aircraft in less than a second or something. Depends on the complexity. But airfoil, anyway, you can get it in a matter of a second or less. So because they are easy to calculate, first of all, that's one good point. But the other point is what you mentioned, which is if the flow is attached and the boundary layers are thin, then the pressure distribution in real life with all the viscosity is actually very, very similar to pressure distribution past an inviscid approximation calculation. So that's the benefit. So let's put that in some words. So pressure drag becomes noticeable only when the boundary layers are thick So what will happen is if you take a case like this where the boundary layer is thick or where there's separation, and if you look at the pressure distribution in viscous flow and inviscid flow, and let's say you have an airfoil and it's at some fairly high angle of attack. So you have some separation. So yeah. So here this is an airfoil that's close to stall. It's getting up to the point where the airfoil is going to stall soon. The inviscid pressure distribution might look like this. But the viscous pressure distribution will be different. So a viscous pressure distribution might look like this, and it will probably have some kind of constant Cp, and the lower surface won't be very, very much different. So when you integrate the inviscid pressure distribution, what drag will you get? This is a high angle of attack case, right? So flow is separating. When you integrate the inviscid pressure distribution, what will be the drag? positive, negative, 0. It will be 0. Inviscid pressure distribution always gives 0 drag, because inviscid pressure distribution doesn't care about all these things, right? This is only in the viscous flow. Inviscid pressure distribution assumes the flow is always attached. I mean, there is no viscosity. So this will give 0 drag, but viscous pressure distribution will give non-zero pressure drag. Obviously, viscous pressure distribution will also have skin friction drag because there is viscosity, right? There's going to be rubbing on the surface of the airfoil. But even the pressure drag will be non-zero. That's because the separated boundary layer or even a thick boundary layer changes the pressure distribution from the inviscid approximation. So when you go to these kind of situations, the inviscid approximation is not really valid because viscous effects have significantly changed the flow. But when you have thin attached boundary layers like this, like low angle of attack general aviation airfoil, whether it's natural laminar flow or not, because the boundary layers are thin, flow is attached, the pressure distribution is practically like the inviscid pressure distribution, and so there is no pressure drag. And so for purposes of lift and pitching moment, you can do inviscid flow. You're getting 95% of the answer with a very simple inviscid calculation. And so that's really powerful, and that's what has actually driven a lot of engineering calculations in aerospace, for aircraft. Okay, I have about a minute, so let's just sort of conclude this topic and then we'll go to the new things in the next class. So in the current example, so skin friction drag is the main contribution. To the total airfoil drag. And because skin friction drag is the main contribution, if we want to reduce drag, that's the contribution we have to attack. And if there is extended laminar flow, on both upper and lower surface, so because skin friction drag is the dominant contribution, the way we can reduce drag at this condition is by trying to design airfoils that have as much laminar flow as possible. So an airfoil like this is an NLF airfoil, natural laminar flow airfoil. By the nature of this airfoil, the pressure distributions are such that laminar flow is supported over a large portion of the airfoil, say until here on the upper surface and until here on the lower surface, and the rest of it is its turbulent flow. In comparison, if you had designed an airfoil like this, and you can, there's nothing wrong except that you will have laminar flow only for a small distance near the leading edge, and then it's large area of turbulent flow. And we saw that turbulent boundary layer has more skin friction. So if this is airfoil A and this is airfoil B, airfoil A has lower CD, and that comes from lower skin friction drag than airfoil B. Okay, so with that we'll stop today and resume on Thursday.